So this number 4 here says a solid sphere, a spherical shell, a solid cylinder, and a cylindrical shell have the same mass, m, and radius r. If they are all released from rest at the same elevation and roll without stopping, which reaches the bottom of the inclined plane first? I think it's the solid sphere. I read something, I don't remember where it was, that said that it kind of gave a similar example, but basically if its mass is out, I mean farther away from the center of mass, then it's going to be slower to accelerate. And so I mean, if it's the more mass concentrated in the center, the quicker it's going to accelerate. So the sphere should accelerate the fastest, especially if it's smaller.
Well, it's not smaller. They'll have the same radius and the same mass.
Yeah, but
you're still right.
If it were smaller, then
yeah. So especially if it's smaller. So the reason for that, so like you said, the more concentrated the mass is towards the center, the quicker it'll get going. Okay, so energy is conserved, right?
Yeah.
So at the bottom of the hill, what kind of energy, or at the top of the hill, so they're all trying to roll down a ramp. At the top, what kind of energy would they have?
They would have potential.
So gravitational potential energy, just MGH. So if they all have the same mass, they all start from the same height, then they'll all start with the same amount of energy, right?
Yeah.
Okay. So at the bottom of the hill, what kind of energy will they have?
Just kinetic.
So just kinetic. So they'll have some from moving forward, like this, but they'll also have some from spinning. There's some energy that goes into that. That's rotational kinetic energy. And it's 1/2 moment of inertia times omega squared. Okay? So which one is going to go faster? Is it going to be one that has mostly this and not very much of this? Or is it going to be one that has more of this?
I think more of the second one.
It turns out,
but I'm not sure.
so this is the speed that's going to win the race, right? Because that's the straight forward, the straight distance.
Yeah.
So the fastest one that goes down the hill is going to win.
Okay.
Not necessarily the one that's spinning fastest or has the most energy. So the highest number we can get here, the better, right? So what does that mean about this number?
The smaller that number is, the better.
Yeah. Okay. So that's why this works this way. Omega is based on the speed, so that we can't really change. But what can we change about this?
The moment of inertia.
Right. Okay. So what's the moment of inertia?
Equal to?
Yeah. Just basic.
I don't know offhand.
Basically, it's the mass times the radius squared. So you'll get a moment of inertia. Say you have 50 kilograms out here. And this is 3 meters. And it's spinning around in a circle. Its moment of inertia will be 50, which is the mass, times the radius squared. Oops. Okay. So it'll be about 450 kilogram meters squared. So that's a higher moment of inertia. So how do you decrease your moment of inertia?
By decreasing one of those two.
Right.
And you can't really change the mass, so you can change the. I mean, if it has a smaller radius, more dense.
Yeah. So the mass of all three of those is the same. So if you bring the radius smaller, but it said that the radius is the same for all three of these. So what's actually changing?
mass is at?
Yeah. So with this one, all of the mass is clear out at the very edges, right? And so as it's rolling, all the mass is multiplied by a radius like this, right? A spherical shell doesn't have quite as much mass on the edges because some of it is on that side part.
So is that just an empty sphere then?
Yeah, it's just an empty sphere.
Okay.
I can't draw it very well because it's hard to draw. But. Okay, so that puts the mass still out from the center, but not exactly. I mean, you still have some just from the sides of it. And then a sphere that's filled in, that mass in the middle is going to be able to spin quicker, and it'll decrease the moment of inertia. So which one has the lowest moment of inertia?
The sphere.
Yep, this one. So that's lowest, which means it'll win the race. So this one's number one. Which one is the middle?
Well, so there's 4 of them. There's a spherical shell. There's a cylinder.
Oh, a solid cylinder.
Okay, I don't know what. Okay, yeah, that makes sense. I got it.
So this one's still a sphere.
Probably the cylindrical shell is probably going to be the slowest.
Okay.
Is my guess. And then the spherical shell is probably going to be the second fastest, and then the solid cylinder will be the third fastest. My guess.
Yeah. So that's a pretty good guess. It's not worried. You don't have to answer about these two.
No, yeah, just the first. No, just the first one. Just which one's going to be the fastest.
But actually, if you have a solid cylinder and a sphere, a spherical shell, the cylinder actually has a lower moment of inertia.
Okay.
So this will come in second. So you can see if you make it a sphere, it makes it a little bit faster.
Why is that?
Because, so with like a cylinder,
I guess a cylinder could only really roll one way, and for all the little bumps, I guess
that's true. But if there wasn't any bumps or anything, the reason for it is that, so with a cylinder, it's long, it's like this, right? But a sphere is round like this, but then it comes down on the insides like that.
Yeah.
So what you've taken is you've cut off this mass out here, and you've moved it closer to the center in there somewhere, right? It's just that it condenses the mass, it brings it closer to the radius. Okay? So spherical is a little faster, and then spherical is a little faster than cylindrical, and then solid is faster than hollow. Okay.
If they're all the same.
Right, if they're all the same mass and they're all the same radius.